So last class we learnt about what is a transducer and what are its important characteristics. Let us recall. A transducer is a device that converts a hard to measure physical quantity into an electrical output. Now we also saw that in a typical transducer you have a sensor element, so which changes something on the element property. We have the physical input, then the sensor element is operated by a signal conditioning circuit. You get an electrical output, either an EMF or a current. It can be even a digital output. And the signal conditioner requires a power supply. So we have this as the transducer. So transducers are also synonymously used as sensors. Right? Whether we call it as a transducer or sensors, we mean the same. And what are the important characteristics that we learned in the last class? One is resolution. Resolution is the smallest quantity, right? Delta input that can give a measurable delta output. This is minimum delta input that gives a measurable delta output. The second is sensitivity of a transducer, which is delta output by delta input. Right? It's like efficiency of a device or gain of an amplifier, output by input. That's the sensitivity. Third, range of a transducer, which is also called full scale, right? Which tells us what the transducer can measure, right? So a range can be unipolar. For example, it could be 0 to 100 kilopascal is the range, or it can also be bipolar, minus 100 kilopascal to plus 100 kilopascal. Right? So if I am measuring P1 minus P2, if P1 is greater than P2, I get plus 100 kilopascal. If P2 is greater than P1, I get minus 100 kilopascal. So it could be range can be not exactly starting from 0. It can be bipolar, or even it could be let's say 20 kilopascal to 200 kilopascal. That is also possible, right? The fourth is proof range, which is the maximum input that it can accept without breaking, right? Normally the proof range is given as overload factor, which is normally given as 1.5 times the range, or 1.5 times full scale, right? And the next one we learned was error. We saw two types of errors. One we'll call the systematic error. The systematic error has two components. Error due to loading because of the transducer itself. The other one is instrument error. Right? We have to be careful. Instrument error, most of the transducer manufacturers gives us full scale error, right? Not the error of the reading. You'll have to be careful when you get full scale error. If the full scale error is 1%, then the error at half the full scale will be 2%. So you'll have to be really careful on that. So we already saw that it's always advisable to measure using a transducer almost nearer to full scale so that the errors are. Uh, the second one is the random error. Random error most of the time comes because of uh, the inherent nature of things. We saw that even if I have a simple resistor, the resistor generates thermal noise because of the temperature, and that would be a random phenomenon, right? Whenever random error occurs, the only recourse is uh, that we take multiple measurements of the same quantity and calculate the average value. And in the last class, we saw that the average value is the best value for two reasons. Number one, the deviation, sum of the deviations from the average value of individual values is 0, and sum of the squares of the deviation is minimum, right? That is why we take the average value. So if I have made measurements theta 1 to theta n, then average value is 1 by n sigma j equal to 1 to n theta j, right? Then once I get the average value, I can calculate the deviation of each value as theta j minus theta bar. So this is theta bar, average value, right? The uh, uh, we saw that the if I represent the actual measurements, this is 1, 2, 3, 4 n measurements, and this is theta average, theta bar, and individual values will be something like this. So I get theta 1, theta 2, and theta n, right? And the difference between the uh, average value and a particular theta is this is d1, this would be d2, and let's say n is somewhere here, this is dn, right? And we already saw sigma j equal to 1 to n, dj would be 0, right? So we have sigma j equal to 1 to n, dj would be 0, right? And we already learned in the last class that it looks like a average value looks like a DC, and this looks like a AC. So I can say RMS deviation, RMS value of this AC quantity is square root of 1 by n sigma j equal to 1 to n dj square, right? That's the RMS value of the deviations. But the RMS value, uh, as electrical engineers, of course, we do understand AC quantity like this when I represent it's. But if you look at the correct mathematics, this is not correct because if I have n deviations, there are only n minus 1 independent values. the nth deviation would be sum of all the negative of sum of j equal to 1 to n minus 1 dj, right? Nth deviation would be dependent on all other deviations. So what is mathematically correct, we call this as standard deviation, and we use a special symbol sigma, is square root of 1 by n minus 1 sigma j equal to 1 to n minus 1 dj square, right? So as long as there is no outliers, there is no uh, bias, you can use any n minus 1 deviations. It's not a very big problem, right? So when I have the uh, random errors, like we indicate the accuracy in terms of systematic error, we indicate the error when I have random error present in my measurement as average value plus or minus deviation. So this could be d max, which means you find out of all the d1 to dn, where d max is equal to d1, d2, d3, dn max. So one particular value will be the maximum value that we take. We take the positive maximum and we take the negative maximum. Normally we put identical. So this is called the maximum deviation. We can also represent it as average value plus or minus standard deviation. And of course we can also say this approximately average value plus or minus RMS deviation. The standard deviation and the RMS deviation are very uh, uh, nearly equal. They can be used as one for the other. But when it comes to the maximum deviation, uh, there are two possible scenarios. When I put it like this, so we can have a maximum deviation as unipolar or bipolar. Let's see what is unipolar. Unipolar means that one side is not permitted. Let me say plus 0 minus d max. So this is unipolar, and a bipolar is, of course, this is bipolar, right? So one side we make it 0 and then say it's no, positive deviation is not permitted, right? And so which means it has to be only on the negative side. It is also possible that I can have theta bar plus d max minus 0, which means negative deviation is not permitted. Where is this used? This is used in most of manufactured quantity where measurements are made, not in really in transducers, but manufactured quantity where measurements have to be made. For example, let's say I want to build a fan, right? So if you look at the fan, you have the stator, this is the rotor, and the fan has to rotate like this. So you have two bearings on this rod, right? So if I look at, I have the fan rod, I have one bearing and another bearing, right? The manufacturer normally says it's a double ball bearing uh, fan, right? So if I look at this bar, let's say uh, this is 2 centimeters, right? And so I have the fan rod, whatever is the length, 1 meter, and the diameter phi is 2 centimeters. Similarly, I have the bearing. Of course, inner diameter must be 2 centimeters. But when a manufacturer makes, there is no way he can make exactly 2 centimeters. Is it possible to make 2.000 centimeter? Not possible, right? So when you give the specifications for manufacture, you say 2 centimeters plus or minus, let's say 50 micrometers, or we call 50 micron. The inner diameter, again here we say 2 centimeter plus or minus 50 micrometer. If you give this specifications, suppose let's say this is uh, plus 50 micrometers and this is minus 50 micrometers, then it will not fit, because the inner diameter of the bearing will be less than the diameter of the so the rod will not go in. So what do? We don't put these specifications. Here I would say 2 centimeter plus 0 micrometer. It cannot go above 0, but it can be slightly less, 50 micrometers. Similarly, here ID I say 2 centimeters. It can go up plus 50 micrometer, but the minus should be 0 micrometer. So we call this as unipolar tolerance. Now I have used another word. Deviation is also called tolerance, and tolerance is generally used uh, in most manufactured quantities, including electronic components. For example, if I want to buy a resistance, right, I have to give specification to the shop wala. Then I say it has to be a metal film resistor. Then I'll have to talk about the wattage, let's say 1 watt, right? And I have to give the tolerance. So tolerance, I say plus or minus 1%. So here the tolerance is bipolar, right? Um, so many times we don't even understand when we have done this several times, right? Except that we this 1% we call it as tolerance without understanding that is actually because it's a manufactured quantity. Random errors will creep in, and I will have to specify the random in terms of deviation. So this is standard deviation, right? So if I now make measurements and plot the measurements as values, and I have a 100 ohm resistor manufactured. Some may exactly have 100.000 ohms, some value will be 101 ohms, some will be 100.5 ohms. So if I mark this is 100 ohms, this is 101, this is 99, this is 98, 97, and if I look at a plus or minus 1%, oh sorry, that's not correct, it has gone to 97. Oh, what happened? It's not erasing, sorry. I'm not able to, ah, oh, I'm not used to this. Okay, now it's gone. Still has not gone. Sorry. So this will be something like this, right? Most value will be close to 100 ohms. So this is not 100, this is 100. Okay. Uh, so the thing uh, is it possible to put this is actually X, this is number of resistors. Let's say I take 100 ohm resistors, 1000 resistors and put here. Maybe I will get 300 resistors, exactly 100 ohms. Some 25 resistors, 199 ohms, and maybe 35 resistors, 1 ohms, and so on. So, is it possible that we can uh, put the a mathematical expression, uh, the uh, in the past people have tried uh, getting uh, mathematical expression for the this particular curve. We call this as an bell shaped curve. uh, if you look at the literature, you will see people have tried to uh, get all sorts of equations, uh, but today we have only uh, one particular curve uh, called the Gaussian curve. Now, if I now take this and I make only 500 measurements, right? I may get something similar to this, but the peak value will not be 300, it may be 158 or 156, right? So, in order to eliminate the number of measurements in representing the large repeated measurements, what we do is we divide by the, right? So, in the y-axis, we put number of times a particular measurement, jth measurement has come by the total number of measurements. So, this again would be the same curve, but the peak would be, for example, it will be here, it will be 0.3, here it will be 0.312, right? So now you see that these two measurements are normalized. This is also 0.3, this is also 0.3, so we can compare. So when I take the number of times a particular value have been obtained, for example, the value of 100 ohms obtained, and divided by the total number, I will get only a fraction, because total number will always be greater than the actual number, right? So, or in other words, what does it say? If I make 1000 measurements, 300 measurements, I got 100 ohms. Or I can simply say the probability of getting 100 ohms when I make 1000 measurements is 0.3. So this quantity I can simply put probability of the jth measurement, right? So then we call this as probability distribution curve, right? So as I said, the uh, uh, there are several uh, uh, functions were tried to fit this curve, but only one has withstood the curve. It's called the Gaussian curve, where I again, this is x, this is y. We put y equal to h by root pi into e power minus x minus x bar whole square h square, where h is the height, this height, that is height, right? So This is the Gaussian curve. Most of you would have learnt about this in the undergraduate course, but it is not a big problem. Now, if I look at it, the average value, right, must be x bar. So if I look at in terms of average value to be x bar and the standard deviation as sigma, then from this equation I can calculate sigma is equal to 1 by h root 2, and uh, the x bar, of course we can calculate x bar. So now I can rewrite this as the same equation. I can rewrite it in terms of y equal to 1 by sigma into root 2 pi, right, e power minus half into x minus x bar divided by sigma whole square, right. So the moment I take measurements, I calculate the x bar and I calculate sigma, then I can draw this particular curve. Uh, the thing is, we keep using this without actually thinking that this is not exactly correct. For example, if you look at this curve, even when x is equal to 0, this still has some probability. It will be e power minus half x bar square by sigma. That will be a small value, it will be there. So it simply tells that I am going to have a curve like this. So it goes to 0 only at infinity, right? Which is not correct. Most of the measured ones will be something like this, right? So you don't expect if when you buy a 100 ohm resistor to have a 0 ohm value. It's not possible. It's not correct also. It's not practical. It is not useful if I have something like that. But as I said, it is impossible to have a mathematical equation for this bell-shaped curve with discontinuities here and here. So we use the approximate uh, the approximate curve which is given by the Gaussian function, right? Uh, Now the uh, in most cases, if you look at the Gaussian function itself, it is still not that bad, uh, because I take x bar and I put plus sigma and minus sigma, one standard deviation away. 68% of all the readings will come x bar plus or minus sigma if I use the curve, right? If I put uh, uh, v bar plus or minus 3 sigma, right? X bar plus or minus 3 sigma, 99.9% of the readings will be within that curve. Only small values go out. So it's still okay to use this curve rather than exactly using this curve. The advantage of this is the moment I know x bar and sigma, I can just throw away all the readings. I can create this nice graph from the sigma and x bar values, right? Uh, Now, when we measure using transducers, we may use that value and compute something, right? Uh, it could be, let's say, I have two quantities. I measure theta 1 degree centigrade and theta 2 degree centigrade, right? And then I calculate theta t equal to theta 1 plus theta 2, right? Um, this we do all the times. Sometimes we take two P1 and P2 and put total pressure P1 plus P2, or differential pressure as P1 minus P2, and so on. So if I add two measured quantities, each one has an error of epsilon 1%, and this is epsilon 2%. What would be epsilon t percent, right? We call this as propagation of errors. Propagation of errors comes into picture only when we try to compute using measured quantities, right? Now if it is uh, systematic error, right? Right. So I have I let us put this as y equal to x1 plus x2, x1 as plus or minus x1% error, x2 as plus or minus x2% error, right? So now I can say y plus or minus delta y is x1 plus or minus delta x plus x2 plus or minus delta x2. Please remember x1% is delta x1, which is the deviation in x1, divided by, error in x1 divided by x1 into 100, right? Similarly, x2%, how do we calculate? Error in x2, delta x1 is x1 measured minus x1 true, right? Divided by x2 into 100%. This we should remember, right? So now if I have delta y by y percent, this would be x1 by y uh, plus or minus delta x1, right? Plus x2. Uh, okay, let me put this in a different manner so that we get me right. I'll delete this. So I take this x1 and x2, x1. So I the whole thing is this, I divide by y. So this is y divided by y plus or minus delta y by y, x1 plus x2 divided by y. See, I have taken this x1 plus x2 here, then plus or minus delta x1 by y plus or minus delta x2 by y. So this is 1, this is also 1, so 1 1 cancels out. So I will have delta y by y, not percentage. I don't know why I put percentage there. I'm sorry, just delete this. So delta y by y, we simply, right, into 100%. That would be y percent, right? Error in y. That would be delta x. I am going to write this as in a slightly different fashion. I will put delta x1 here. I am going to put divided by y here. This y is coming here. So I am putting x1 in the numerator, x1 in the denominator, and multiplying by 100. Please remember I have multiplied the left hand side by 100, so right hand side also. Similarly, I can put divided by y delta x2. Here I am going to put in the numerator x2, denominator x2 into 100%. Now we know what is this? This is x1%. What is this? X2%. So I can now write y percent is equal to x1 by y into x1 percent plus x2 by y into x2 percent. So the error in x1 affects y to the extent that x1 is part of y. Similarly, error in x2 affects y to that ratio. What amount of y is formed by x2, right? So if I now have y is equal to x1 plus x2 plus x3, where x1, x2, x3 are measured variables with error x1 percent, x2 percent, x3 percent. We are talking about systematic errors, not random errors. So we'll have to be very careful with the type of errors. Then we can write y percent error in percentage error in y would be x1 by y, x1 by y into x1 percent plus x2 by y into x2 percent plus x3 by y into x3 percent, right? So we can extend this to any, right? Now we take a second, right? Y is equal to x1 into x2, right? So we can measure the torque and the angular speed omega. Then I can calculate the mechanical power as omega tau, right? So where tau is the torque, omega is the angular frequency. So both are measured values. They will have errors. So x1 as usual has plus or minus x1 percent error. x2 has plus or minus x2 percent error, right? So what happens now, right? So I will have y, right, in plus or minus y percent error. So if I now expand this, what is x1 percent? I can write this as x1 whatever is the error plus delta x1 into let me again remove this. This is y plus or minus delta y into x2 plus or minus delta x2, where delta x1 and delta x2 are errors, not percentage errors, actual errors. We can write as, if you remember, x1 percent is delta x1 divided by x1 into 100. So x1 percent into capital X1 by 100 would be delta x1. So I can write this here, x1 into x1 percent divided by 100 would be delta x1. So we can calculate this. So y plus or minus delta y. So I multiply these two, x1 into x2 plus or minus delta x1 into x2 plus or minus delta x2 into x1 plus or minus delta x1 into delta x2, right? x1 x2 is nothing but y, so this can be cancelled. So I have plus or minus delta y is equal to plus or minus delta x1 into x2 plus or minus delta x2 into x1 plus or minus delta x1 into delta x2. Now I divide by y, multiply by 100, so that will give me y percent error. So on the right hand side also I divide by y, multiply by 100, divide by y, multiply by 100, divide by y, multiply by 100. Now I take this particular value. So this is I put x2 by y this is delta x1 into 100, right? Once again we do the same trick. I put x1 on top, x1 at the bottom, right? So that would be the first entry. So plus or minus, again this is plus or minus, uh, x1 by y into delta x2. I divide by x2, multiply by x2. So I'm not changing anything. x2 by x2 will be 1. So into 100. And the last one would be plus or minus delta x1 into delta x2 divided by y. I am going to put uh, okay y as we already know what is y, x1 dot x2 into 100, right? So this of course is 1, this is also 1. Please remember what is y, x1 multiplied by x2, right? So this is nothing but x1%, this is nothing but x2%, again I have to put plus or minus x2%, and this would be, if I look at this, plus or minus x1 dot x2 by 100%, right? X1 and x2 are errors, they will be small, so this can be neglected. So we can say approximately equal to 0. So I can write this as plus or minus of x1% plus x2%. So if I take y is equal to x1 into x2, I multiply two measured quantities, the errors simply add up. It doesn't matter if I put y equal to x1 by x2, then also the errors will add up, right? The errors will be x1 plus x2%. I am not doing this, you can do it as a homework, uh, and we will see later. Uh, so of course we can do this whenever we use measured values and calculate something else. We can uh, use the uh, long-winded method of calculating this, but it would be nice if we can have a formula, right? What is that formula? Let me say y is a function of uh, x1, x2, x3, dot dot dot, where x1, x2, x3 are all measured variables with x1%, x2%, x3%, and so on. Let's say xn%. Now, if I use perturbation theory, delta y is dou f by dou x1 into delta x1 plus dou f by dou x2 into delta x2 dot 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 dou f by dou x n into delta xn, right? Now again I multiply, divide by y, and multiply by 100. So this would be y%. So this is dou f by dou x1. I am dividing by y. I get delta x1. We do the same, x1 in the numerator, x1 in the denominator into 100, right? Uh, Plus dou f by dou x2 divided by y, delta x2, again I put x2 in the denominator, x2 in the numerator, into 100. So I can do this till I get dou f by dou xn, again divided by y, xn delta xn by xn into 100. So now I can write this as y percent is equal to, we know this is x1 percent, right? So x1 by y into dou f by dou x1 into x1 percent plus x2 by y into dou f by dou x2 into x2 percent plus dot 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 dou f by dou xn uh, into xn by y into xn percent. So this formula we can use if I have y as a function of x, right? Uh, let's put a simple example. Let's say I have y equal to x square, right? Where y I am calculating as a square of measured variable, x as plus or minus x percent as the error. Now if I use this formula, I allow to differentiate y with respect to x. So y percent would be 2 uh, x into x by y into x percent, or I'll get 2x percent, right? Similarly, if I have y equal to square root of x, where x has x percent error, I will put capital X here so that we don't get confused. So this is capital X, right? Small x. So this you will see x percent divided by 2. Y percent, in this case, y percent would be x percent divided by 2. You can work out. Um, I have uploaded the notes for what I am teaching in the last two classes onto Moodle. You can download and study. Okay. Um, so this is for systematic error, right? Propagation of systematic error, right? Propagation of random errors, right? We will see in the next class, right? I complete my lecture today. See you on Thursday morning.